Next up is Marc Stevens. Is it Stevens?
It is.
Okay. Who's a senior engineering consultant with C-FER Technologies up in Canada. C-FER is doing a number of working in partnership with the industry up there, looking at a number of technologies, but Marc's name jumped out at me because I share the C-FER circle model with people all over the country. If you realize that, it's how you determine impact areas around natural gas pipelines. And guess who drafted that famous C-FER, that model that developed the C-FER circle? So I was impressed when I saw Marc was going to be here, and he doesn't know how often I have shared that report with people to try to help them wrap their heads around risk around natural gas pipelines. So Marc, you're up, and there it is.
Thank you, Carl, for the introduction. Good morning. I'd like to take the opportunity to thank the Pipeline Safety Trust for the invitation to talk to you today about some of the ongoing research that my company is doing on external leak detection technologies. I've got a disclaimer or an apology to make, or maybe I'm going to manage your expectations if I can with respect to what I can or will say. Some of the research I'm talking about is still ongoing, and frankly, the findings of that research is confidential to the participating companies, at least for the near term. So whereas I can't talk about the details and what we're finding explicitly, I think it's worthwhile to give you a flavor or feel for the kind of initiatives that industry is undertaking to evaluate what works, what doesn't work, how well it works, so that they can make effective choices on what kind of complementary leak detection systems to consider deploying on their pipelines to enhance pipeline safety and environmental protection. And so my focus is on some of the efforts that we're currently working on their behalf with relate to detecting leaks from liquid hydrocarbon pipelines. Now, David provided an overview of kind of why people or industry is looking at alternative techniques. And I'm not going to belabor that point, but maybe I'll summarize a few of the key points echoing what David said. So conventional internal methods, a lot of which use computational methods to try and make inferences from looking at what's going on inside the pipeline in terms of pressure and flow and stuff, about whether or not conditions are not what they should be and perhaps indicative of loss of containment. And those systems work pretty well for the larger release events, but for very small leaks, there's a threshold or a flow below which they're not effective. And the reality is that small leaks, if they go undetected, can generate significant spill volumes, and obviously that's a problem. So there is interest in alternative technologies, and a lot of them are under this umbrella of so-called external leak detection methods, because you're looking outside the pipe instead of in as a way to figure out what is going on. And the reason you want to do that, as David has suggested, is that they provide a complementary way of assessing whether or not a leak has occurred, and that complementary nature provides redundancy and enhanced ability, therefore, to detect leaks. And they have the potential, according to the claims, to address that blind spot for slow or small volume leaks that would go undetected using some of the conventional methods. Now, many of these so-called external leak detection technologies are new and evolving, and the fact is the performance capabilities of a lot of those systems has yet to be established or verified. And it's also difficult to verify how those systems perform through field trials or pilot projects because, of course, pipelines do fail, but not that often. So the incident database of leaks on monitored pipelines is very limited. And that limited data makes it hard to figure out how good or bad these systems are. And attempts to simulate leaks out in the field on realistic pipelines is also problematic, especially if you're dealing with liquid hydrocarbons, because operators don't want to release liquid for the purposes of demonstrating whether their technologies work or not. So another approach is to try and do this in a laboratory setting, and that's kind of where we've stepped in with some of the projects we're working on. Now, there's a lot of different methods out there, and this is not a comprehensive overview of those technologies, but it kind of splits things into two groups for the purposes of what I want to say. One family I'll call as continuous monitoring involving in-ground or buried systems, basically cable or tube-based systems running a length of the pipeline, buried adjacent or in some cases on the pipeline for the purposes of trying to detect liquid product releases when they happen. There's a set of technologies that ride on top of fiber optic cables, and they exploit the fact that the light transmission or light reflection capability of these optical fibers changes in response to vibration, temperature changes, or strain. So they can take that and flip it around and make optical fibers effectively a long linear sensor for hearing the acoustic noise generated from releases, sensing the temperature change when warm oil gets out into cold soil, or actually feeling the deformation of the ground if it gets pushed out of the way by a liquid release. And fiber optic cable implementations are attractive because, as David has suggested, fiber is being deployed a lot these days on pipelines, in part for communication purposes, moving information up and down the pipeline. There are also applications for so-called encroachment monitoring. And if these fiber optic cables can also serve purpose for leak detection, that's an added advantage to that sort of deployment scheme. But there are other cable-based systems that are on the table for consideration. Some fall under the label of electrical cables. Effectively, it's an electrical cable for which the electrical properties change when liquid hydrocarbons come in contact with them. So if you're sampling the voltage and currents passing through these cables, changes can be indicative of them being contacted by hydrocarbon liquids. And there's another class of linear systems that employ permeable tubes. The idea is that if a hydrocarbon liquid spills out of the pipe, it loses the confining pressure, and the volatile liquids flash off, and the vapor then migrates through the soil. These tubes are permeable to those vapors. The vapors collect in the tubes, and if you sample the vapor in the tubes and you find trace amounts of these trace elements, the implication is there must be a leak. So there's these linear distributed assets that are buried in the ground for leak detection, and then there's the other class of external systems that I'll put into the periodic inspection category, often involving deployment either airborne or on satellites. And the idea is that they fall into a number of broad categories. I'm oversimplifying, but in the interest of just trying to paint the picture. There's the visual inspection techniques that use manual or automated means to process high-resolution images to look for changes that might be indicative of a leak that's ongoing. There are sensors that are meant to try to detect the trace amounts of the gases or the vapors that are released by these liquids as they break down in the atmosphere above the right-of-way. There are systems that are looking to detect the temperature changes at ground surface due to these warmer liquids spilling into the ground, and then so-called light detection and ranging or LiDAR systems that are looking to see or detect subtle changes in the elevation of the ground. Again, the idea is if the oil comes out, maybe it pushes the ground out of the way, pushes it up. If they can sense those changes, that might be a way to make inferences about what's going on. And we've got two separate programs ongoing, one focusing on the buried distributed systems and another focusing on selected technologies for airborne leak detection. And I want to focus on the first and give you a flavor for the second in the time that I've got. So the first program is a joint industry program, and our research partners in this initiative are Enbridge Pipelines, TransCanada Pipelines, and Kinder Morgan Canada. So working with them, we designed a program to experimentally evaluate selected cable or tube-based technologies for detecting leaks from liquid pipelines. And the focus is on fiber optic cables for so-called distributed acoustic sensing or distributed temperature sensing, or a combination of the two. We're looking at vapor sensing tubes and hydrocarbon sensing cables. So these cables, about as big around as your finger, are deployed either through direct burial or inside conduit, running the length of the pipeline, and their deployment ranges vary considerably from miles to tens of miles. So these long cables can be deployed and detect along significant lengths of pipeline, and they're therefore suitable for transmission pipeline type applications. And what we're trying to do is independently establish data that can be used to help determine what the performance capabilities of these technologies is, so that, again, operators can make informed decisions on what to pick and what applications are going to be better suited to the technologies that are available to them. A side benefit of this is it's helping the vendors of the technology benchmark their systems and make improvements to how their systems work, how they respond to release events, how to avoid false alarms, that sort of thing. Now, I said we were going to do this experimentally, and our focus has been to try and do it in as realistic a way as possible. So we are looking, because these pipelines are buried in the ground, we're trying to simulate realistic soil conditions, use representative and useful sensor placement configurations. We're looking at simulating realistic temperature differentials between the oil in the pipe and the surrounding soil. and realistic release events. So we're trying to blow oil out of little holes in the side of a test pipe at pressures that are representative of pipeline operating pressures, through holes that are representative of the holes that are associated with small leaks, and to generate flow rates that are consistent with those hole sizes and pressures. And last but not least, we're interested in acknowledging the fact that leaks don't happen at the bottom. They can come from the bottom, the side, the top, all around. So we're looking at what differences releases in different directions make. Now, this test setup is also designed to provide, to the extent possible, identical or at least similar conditions for all the technologies being evaluated. So it's sort of a round-robin comparison where everybody is seeing the same events, and you can then objectively compare what the different technologies do or don't see. And it's all being done in a way, we hope, to make sure that the vendors don't know what's going on during the testing. So it's blind testing, and I'll explain that a little bit later. Last but not least, the consideration and design of the testing program is that we are using real hydrocarbon liquids as the fluid that we are releasing from our test pipe, and there are safety concerns, fire, explosion, long-term impacts on workers. So we're trying to handle those products safely. So the apparatus has been designed to let us do release simulations for any low vapor pressure liquids. Our current focus, however, is on dilbit. Now, this is the apparatus. It goes by the acronym ELDER, which is meant to refer to External Leak Detection Experimental Research. I guess if you attached A to it, it would become ELDERA, but ELDER was preferred, so that's what it's called. It effectively consists of a soil containment tank. It's the green box you can see in the photo. It's about 8 feet wide, 8 feet deep, 24 feet long. Into that, we can put a segment of line pipe. In our case, we're using 24-inch diameter pipe, so we can place pipe, soil, and sensor cables inside that green tank. We then receive a product. We put it in one of those silvery vessels. We store it, we get it up to temperature, and then we use either pumps or our pressure vessel to pump or blow this fluid through piping into the test pipe and out of orifices that we have installed at various points along the lengths and around the circumference of the pipe to basically discharge into the soil and into the area where the sensors are placed. We're worried about safety, so we've got a berm around the outside just in case everything goes wrong and we get leakage out of the tank. We have a tent. You can see the frame of which in the upper right that we extend over the apparatus. So basically we can run these tests in a secure environment in our lab and simulate the release events that we're aiming to achieve. So again, the end purpose is to blow oil through little holes in the side of a pipe. Now, this is a commissioning test. We're blowing water. It ain't water, it's oil, and that pipe will be surrounded with compacted soil and sensors when we're actually doing the tests. Just a few comments on the soil and sensor placement. Again, we want to simulate the environment that the pipe's really in, so we're placing the soil very carefully in lifts to get the compaction right so that we can represent the heavily consolidated soil below the pipe and the less consolidated soil in the backfill material on top. With respect to sensor placement, we're looking at what the sensor mechanism is, where the vendors think their cables should go. We're looking at where the pipeline companies think they realistically could put these things. And we're gaining insight from the testing we've done. I've got a matrix of dots. We're not putting cables at all those locations, but that's kind of an indication of the different locations that we're considering. So we're putting these sensors in the soil as we lift or place the lifts. And just to give you a feel for the process, here's one of our technologists. He's loading the pipe into the tank, which means we've already placed soil in the bottom. You can see the soil bags, those 1-yard bags in the bottom. One bag goes in at a time, rolled, compacted. The pipe goes in. We then continue filling this tank with soil, placing the sensor cables, packing it down until we get the thing full and we're effectively ready to go. We then put the lid on the tank, and we then slide the tent enclosure across it so that we're sealed in. And then we get all the vendors on site and we run a week of testing. So effectively we stage multiple release events over the course of a week. They spend way more time than they want to in those little cubicles you can see in front of the lower left-hand photo. That's where their systems are actually set up. They're hooked into our cables that run inside the tank, and they basically log for the course of the week what their systems say. And at the end of the week, we ask them to tell us when their system went into alarm. So we compare all their alarm logs to our release events and make inferences about which events they saw, which ones they didn't, and how long it took for them to see those events. And as I said, I can't go into details about what we found, But I can say the following, that the leak detection capabilities of the various technologies that we're looking at do vary. Not only do they vary from technology class to technology class, but they vary from vendor to vendor. Some technologies and vendor offerings are more mature than others. And they vary both in terms of what the detection threshold is and how long it takes for detection to occur. And perhaps not surprisingly, the ability and time to detect is a function of where those cables are relative to the pipe and where the leaks are coming out of. And in terms of what exactly are we finding, again, I can't be terribly specific, but to the extent that there's a number out there that says conventional internal systems may work all the way down to flow rates of the order of 1% of routine pipeline flow rates, there are certainly systems that we've evaluated that can detect leak rates that are much less than 1% of flow rate. So this is all very promising. These technologies do have the ability to detect very small releases under the right conditions with the right kind of system. Just a few quick comments on our airborne initiative. So instead of looking at sensors in the ground, we're looking at sensors that are meant to fly over top of the pipeline. And again, we're looking at systems for detecting releases of hydrocarbon liquids before they reach the ground surface. And our technology focus is on technologies that employ laser absorption or flame ionization or thermal imaging. And I won't belabor the details of how they work, but the top two effectively look for hydrocarbon vapor at low concentrations in the atmosphere above the right-of-way. And the last one is just looking at how the ground temperature changes and whether or not those temperature changes are indicative of a leak. And we're doing two things, not just evaluating the technologies, we're trying to develop models that will help us predict how the volatile liquid fraction of the spill migrates through the soil, how quickly it permeates up through the ground and into the atmosphere, and how those concentrations in the atmosphere vary with elevation. Because these systems don't ride on top of the ground, they ride up in the air. So if they're riding up high, there is some concentration decay of the vapor plumes as you go up. So what they're chasing are very small concentration levels. So we're trying to figure out what concentration levels they should expect to see. And last but not least, we are deploying their sensors to see what they do see. And this research is also being done with funding from the same three companies, Enbridge, TransCanada, and Kinder Morgan Canada. So without going into details, because I don't have enough time and I'm probably pushing my time limit already, we're doing modeling to look at how the temperature in the soil changes when the warm oil gets into the cold soil. We're looking how the vapors permeate through the soil as a function of the soil properties and how much vapor reaches the surface and what that vapor flux rate through the surface is. We're also looking at how those vapor clouds disperse in the atmosphere downwind and with elevation, all for the purposes of trying to figure out what kind of products they should be looking for and what kind of concentrations they have to be able to detect. Now, models are all fine. I like building models, but people wonder whether the models are accurate. So part of the process is try and validate these models. One way we're doing this is we've done some releases in the tank that I showed you before. Some of the current research is piggybacking on that because effectively we put those silver domes on top of the soil for a few tests and we've been sampling the vapor so that when a release happens underground, we can also sample the vapor to see what's coming up and how quickly it's coming up. And that we can use to calibrate the models we're using to predict what those vapor concentrations and vapor flow should be like. And so this is helping us to validate and improve the models we're using to predict what should go on. And then last but not least, we're taking this stuff out into the field and checking the vendor's capabilities. This is perhaps not the easiest picture to see. This is a rendering of an area the size of a football field. We've got points on the ground where we're going to release the appropriate gas species at a realistic flow rates into the air. We deploy on this boom that you can see in the upper right-hand corner, the sensor packages, and we're looking to see what they see. Do they go into alarm and how quickly does that happen? So that's kind of what we're doing on the airborne side. And the work that we've done on sampling or evaluating technologies meant for sensing vapors in the atmosphere is currently ongoing. We're about to start up with a program to evaluate the sensors that are intended for thermal imaging. And these are very much a work in progress, and we really don't have a lot of information to share at this particular time. And again, I apologize for lack of specificity, but I just wanted to leave you with a sense that there are industry partners who are spending significant dollars and significant effort to try and figure out which technologies are going to work, how well they work, so that they can then make decisions on how and where to deploy them to enhance the safety and integrity of the pipeline systems that they're trying to operate. And with that, I shall stop. Thank you for your attention.